Okay, so we're gonna look at names. So the first thing we need to do is load a bunch of names. So we get the whole first. Actually, I need to lay the foundation. So this is a pretty sensitive talk for many people because gender is a hot topic these days among people who are often choosing their own gender. And what I'm talking about is the amount of masculinity or femininity in a name, not in a person. I'm not talking about any. This is taking from birth certificates and first names only on those birth certificates, and whatever the doctor assigned their sex to be, not their gender, but their sex. And so, have not found any other sexes in the database mentioned other than female and male. But there do exist other sexes and other designations that doctors are assigning to babies. So this is an incomplete data set, and it's not intended to be associated with people anyway. It's only about the name. So because all words have this thing called have nesses in them, I like to call it. So like humanness or animalness or color, redness or blueness, all words have a sense, some connotation about various things in them. And so we're measuring things like maleness and femaleness. And these are not necessarily opposites on any kind of a scale. So these are just perpendicular elements in a vector is what we usually use in order to characterize a word. So if you've heard of word vectors, all of the components of a word vector are perpendicular to all of the others. And so it's not that, so we're just measuring two dimensions, and we could even measure other dimensions like how modern the name is with this data set, because we have the year that the name was popular. But anyway, let's get in the data set. So what we've got here is I've got a little script here that's just going to search the path to find where this file exists, baby names by region. We're going to load it with pandas, read CSV into a data frame. Then we're going to sample it using a random seed in order to make that a consistent sample. I don't know if you've seen this before, but in Python, you can put an underscore in large numbers in order to divide into whatever groups of zeros you like in your culture. But so thousands, so 10,000 were sampled here. So we only need, and there are millions of different, millions of unique names in this data set. And there are hundreds of millions of counts of babies in this data set. So we only need a very small amount to get really high accuracy on this problem of identifying the gender or the sex of a name. So now that we've got these names, so these are the kinds of names that are in the data set that we've pulled out. I'm having trouble with this little bit here, but what it's doing is we're pulling out a sample of the names. So these names are not unique in this data set because it's listed by state and year. So there'll be a unique name for each state and year in the database for each census year, or each year of birth or whatever when they gathered up all these birth certificates. And so we need to find all the unique names, and because we're only interested in the name itself, we're not trying to predict the state, and we're not trying to predict the year. So we're just interested in the name itself. So we've gotten all the unique names out of these 10,000 samples that we got out of this database. And so this comes up with only 3,600 unique names in our training set and 4,000 overall of those unique names out of 10,000. So that means like about 40% of the names are unique or duplicates, or 60% are duplicates. That's another way of looking at it. If you just randomly sample the data set. Now let's look at, so we gotta set this is train. We need to, in order to avoid training it on the same names, we're going to ask it about. We're going to ask it about names like Maria, which is in there. We're going to also ask it about my name, which is not. and it's not in the training set nor the test set. And there's some other names that Kamal and some others that have worked with me. We're going to ask it about those names, and it's hopefully going to get those right if I do everything correctly. So let's make sure. What I'm going to do actually is I'm going to copy everything rather than trying to pick and choose what worked. I'm going to pull out all the stuff that did work in the past. Let's see how far we get along here. So this works, and now this works. So we've got it indexed by name. We need to index the data frame by name, I think. So df is train is this guy, and that was merged. So df, we're merging the training, this data frame that has trues and falses for whether or not it's going to be in the training set or not. We're merging on the name. We're merging with df. Okay, so I need to. That's where I messed up. df.index or set index. Maybe I should. I'm going to take out the. I'm going to take out the setting of the index here. This is probably the problem. Start over. Create a fresh. df is train. Let's not set the index, and let's see if. Darn. Okay, let's start the whole thing. Okay, now we're getting somewhere. I wonder if we can merge. We're going to find out. Great, we can. Let's make sure we haven't ended up. We don't want it to merge twice. Let's make sure. So we've got about 90% in our training set and 10% in our test set. Now let's try to do that. We're going to first try to train a model that only uses the length of the name in order to guess so longer names or shorter names. We're going to find out whether those are more male or more female. Later, we will create a vectorizer that will do it more, get much higher accuracy, obviously. So let's now train that. Oh, we already got the model here, so now let's do a model.fit. Model.fit x comma y. Great. Model.score. We didn't exclude the training set in this case. I'm trying to make sure that it's going to work at all before I get really rigorous. So it got slightly better than random accuracy. We need to do one more thing to make it a little better. Class weight equals balanced. So that way, if there's more or less entries of one or another, and actually this should help a little bit. And then we're gonna ultimately though, we're gonna use the counts that are in the database for the number of people in those states that were born with that name, and in the final model. So you can see that we're not getting much accuracy, and I'm going to move on to the more interesting model that actually uses a vectorizer. So we're going to import it and create it, and let's get all of that going. We're going to use n-grams between 1 and 3. And we're also using a character-based n-gram analyzer. So obviously we only have one word, so we can't use words as our tokens. So we're going to use the sequences of characters. We're going to also set lower equal to false. That way it will recognize when a letter is the first letter. Lowercase, I think, is how it says it. Let's see if this works. Make sure that works. Yeah, great. So we got the lowercase. Now we can say vectorizer.fit. So this is going to count up. Oh, was I not sharing my screen?
No, you're good.
Okay, great. Somehow my Zoom told me that I'm just now sharing my screen, but whatever. So let's see if we can fit it to the training. In this case, we're going to be a little more rigorous. Hopefully this is trained. The vector of bools and falses will work with the df. Actually, I want to check that out first. df.head. Let's make sure that those two guys have similar number. Yeah, good. We both have numbers on the index. So now let's see if we can do a fit. No, we can't. This is what I was worried about. Unaligned Boolean series as indexer, index of Boolean series and index of objects do not match. Okay, so somehow the is train ended up with a different index. Yes. So I never set the index to be equal to the df dot index. Let's see if maybe I can just do that straight away. Df is train dot index equals df dot index. Let's see if that works. Cool. And now let's retry that little bugger. Woohoo! Okay, so now we're in business. We have a model that's fit on the n-grams from 1 to 3. Oh, we have a vectorizer that's fit. So this will create this. What you can do with a vectorizer is you can then turn it into an n-gram vectorizer when we do transform on any kind of string. So Amy, this is gonna be a really simple one because it only has 1 trigram and 1 2-gram and or 2 2-grams and 3 1-grams. Let's see if that works like I hope it will. Vectorizer. Woohoo! It's unfortunately it's sparse, so let's make it dense so that we can actually see it. There we go. So it's a vector. It has a lot of slots though for all the possible trigrams that exist everywhere. Fortunately, capital A is at the very beginning. So we got at least a count of, but this gives you an idea what it is. I'm gonna show you more better representations of these vectors later on. Just wanted to give you an idea what they are. So we're gonna use, so that's what we're gonna train the model on. So let's create those vectors based on the names. We're going to create it for all of them, not just the training set. So it's okay. It's legal to go ahead and create vectors for everything that you've got, because we didn't even tell it about the trigrams so there'll be some trigrams that exist in our test set that they didn't even know about, or it's possible at least that that's the case. Let's see. And now we're going to go to, we're gonna take those vectors are sparse, so we're going to create a sparse vector frame. So this is a really important tool. Let's find where from sparse. I need to find how I did this. Dot from sparse. Let's look for underscore sparse. Where are you? I know you're here somewhere. Because that D-type sparse, I don't think that line worked. There it is, sparse. Here we go. We're going to use this PD data frame sparse from sparse matrix. Keeping it sparse helps it train super fast. Let's find where PD data frame does. Find data frame dot sparse. I don't like this new user interface from my browser. Doesn't like this is the first instance. Okay, fine. We're going to go ahead and I'm going to go ahead and do the fitting of the model. Okay, it looks like we're running low on time. Let's see if this even works. Okay, looking pretty good. Only took 2 columns of that. We can add some column names to it. Let's see if this works. Great. We're getting there. We're getting there. dfvex.index equals name. So we're going to have the names associated with those vectors. And then, nope, we need to do it this way. And now, I'm sure it's still looking good. Okay, great. We're starting to be able to see. So these are the name here. I've transposed it, so you get to see the trigrams on the left-hand side and the names on the right-hand side. There's that Brittany name that we had before, and we can find that vector for Amy like we did earlier. And this is all just exploring around, so we make sure that we're working with something that makes sense. Make it one last time there, and now we'll do the x equals dfx. Oops, x equals dfx. Yeah, the whole thing, not just the is train. X equals dfx. We got a x dot head. Okay, so we got all our names and we got all our vectors, and now we can finally fit a model. So model dot fit x comma y, because that that would be on the whole thing. I wonder if this is going to work. Because we have the name in the index, it's not going to work, I don't think. So I'm going to say x dot index equals name equals df name, perhaps. No. Okay, I'm gonna have to bail, and once more we're gonna have to hold off until Saturday to see the conclusion to this great episode. But the code's all here. It's in the repository. I will put a link to the repository. It's in NLPIA2 on GitLab, and it correctly predicted Kamal's name and or the sex of Kamal as he was when he was a baby, and it's the same as it did for our made up name, Cindy, for our imposter syndrome bot. So it works pretty well on at least the ones we gave it, and on the test that it gave us like 99% accuracy. So pretty remarkable, and a lot of fun. And we can do a lot of other stuff like estimate the age or the state, or sort of like, is it a Southern name? Is it a Northern name? Is it a West Coast name or an East Coast name? So lots of fun stuff you can do with this data set and with words in general. So look forward to releasing some of this material in natural language processing in action soon.
Any questions for Hobson?